A random variable has the normal distribution with mean mu and variance sigma squared if it has the PDF f of x equals 1 over square root 2 pi sigma squared e to the minus quantity x minus mu squared over 2 sigma squared, which is certainly the most complicated of probably the standard random variable distributions that we've looked at so far. But it will be a little bit easier to work with than it looks when we start working with them. So we say that x has the normal mu sigma squared distribution. Remember that this is the mean is mu, and sigma squared is the variance. And I also want to point out that there's no closed form CDF for the normal distribution, so don't try to integrate it over a particular interval, because you won't be able to find a closed form formula for the integral. The first thing we want to do is verify that this thing is in fact a PDF. So it's clear that f of x is bigger than 0 for all x, since 1 over square root 2 pi sigma squared is positive, and e to the minus x minus mu squared over 2 sigma squared is e to some power, and e to a power is always positive. So we need to show only that the integral from negative infinity to infinity of f of x dx equals 1. The first step is to substitute x minus mu for x. That will eliminate the mu in the exponent. So when we do the substitution, we also are substituting dx for dx, and we get 1 over square root, oops, there's a pi missing here, so this should have a pi, 2 pi sigma squared e to the minus x squared over 2 sigma squared dx. The next thing we're going to do is compute the square of the integral, rather than the integral itself, because that actually turns out to be easier. And so since we're trying to show the integral is 1, it's enough to show that the square of the integral is 1. And if we square the integral, that means we can write the integral times itself. Right? That's what a square means. X squared means x times x. And for the second integral, we're going to do this trick where we just substitute y for x. So it's 1 over square root 2 pi sigma squared e to the minus y squared over 2 sigma squared dy. Now, since one integral is over x and the other integral is over y, we can combine them into a double integral. So we're integrating from negative infinity to infinity dx, and from negative infinity to infinity dy. And we're integrating e to the minus x squared over 2 sigma squared times e to the minus y squared over 2 sigma squared. And this square root of 2 pi sigma squared, I just pulled both of them out, and since each has a square root, whenever they're multiplied together, it eliminates the square root. So we get a 1 over 2 pi sigma squared out front. Then, doing a little bit of algebra, we can combine these two exponents. So we have minus x squared over 2 sigma squared and minus y squared over 2 sigma squared. So it's minus x squared plus y squared over 2 sigma squared. Now we can substitute for polar coordinates. So x squared plus y squared could be substituted for r squared, and this dx dy becomes r dr d theta. So the integral from negative infinity to infinity of x and y becomes the integral from 0 to 2 pi d theta, and the integral from 0 to infinity dr of e to the minus r squared over 2 sigma squared times r, where this r comes from the r dr d theta. Now we're going to substitute u equals r squared, which means that du equals 2r dr. So this r dr gets absorbed into a 1/2 du, and this e to the minus r squared is e to the minus u. So now we're just integrating 1/2 e to the minus u over 2 sigma squared du from 0 to infinity. So we'll end up dividing by a 2 sigma squared, which would put the 2 sigma squared in the numerator. So it's, and this should be minus 2 sigma squared, oops, please forgive a couple of typos, e to the minus u over 2 sigma squared. Whenever u goes to infinity, this goes to 0, and then it's minus, and we plug in u equals 0, which gives us, well, the 2's cancel, and this should be sigma squared. So it looks like I have a few typos to fix up. But once we get here, we're integrating from 0 to 2 pi sigma squared d theta, which just is 2 pi sigma squared, and that cancels with the denominator, and that leaves us with 1. So in fact, the integral from negative infinity to infinity of f of x dx does equal 1. Next, we want to show that the expected value of x is mu, which was what we claimed at the beginning, but we haven't shown that in fact it's true. So we're going to find this by direct computation. The expected value of x is x times f of x dx, evaluated from 0 to infinity. And what we're going to do is substitute y plus mu equals x. And in this case, dy, it's a plus sign, this would equal dx. So we end up with y plus mu over square root 2 pi sigma squared e to the minus y squared over 2 sigma squared dy. Now we're going to split up this integral over the y plus mu. So we have a y over 2 pi sigma squared dy plus a mu over 2 pi sigma squared dy. And on this integral, we can pull out the mu. So we're going to compute each integral in turn. First, we're going to compute this integral. So we have this integral from negative infinity to infinity of y over square root 2 pi sigma squared e to the minus y squared over 2 sigma squared. And we're going to split this integral up from negative infinity to 0 and 0 to infinity. Now in this first integral, we're going to substitute minus y for y. So that's going to become the integral from 0 to infinity of y over square root 2 pi sigma squared e to the minus sigma squared over 2 sigma squared dy, and then plus the exact same integral. So these two integrals cancel, and we end up getting 0. For the second integral, now we're going to compute this one. The integral of 1 over 2 pi sigma squared e to the minus y squared over 2 sigma squared dy equals 1, because this is just the PDF of a random variable, a standard normal, a normal random variable with mean 0 and variance sigma squared. So it evaluates to 1, and this is mu times 1, which leaves us with mu. We won't compute the variance of a normal random variable here, but the variance is sigma squared. To see that computation, or at least one way to compute it, you can jump ahead to the lesson on moment generating functions. A standard normal random variable is a normal random variable with mean 0 and variance 1. So the PDF, by plugging in sigma squared equals 1 and mu equals 0, is 1 over square root 2 pi e to the minus x squared over 2. Standard normal random variables are very useful for computations. And they're very useful because for any normal random variable x that has mean mu and standard deviation sigma squared, you can transform x into a standard normal by subtracting the mean and dividing by the standard deviation, sigma. So this sigma is not a typo, that is on purpose. So let's let y equal x minus mu over sigma. And let's let f of x be the CDF of x and f of y be the CDF of y. So by definition, f of y is the probability that y is less than or equal to t, or in other words, that x minus mu over sigma is less than or equal to t, since y equals x minus mu over sigma. And rearranging this algebraically, this is the probability x is less than or equal to sigma t plus mu. Which is, since this is the probability x is less than or equal to this number, the CDF of x evaluated at sigma t plus mu. So we've shown that f sub y of t equals f sub x of sigma t plus mu. Now we can take the derivative of both sides to convert them to PDFs. So the derivative of the CDF of y is the PDF of y, and the derivative of the CDF of x at sigma t plus mu by the chain rule would pull out a sigma. So we get sigma f of x sigma t plus mu. And if we plug in the PDF of x, since x is normal with mean mu and variance sigma, we get sigma times 1 over square root 2 pi sigma squared e to the minus sigma t plus mu minus mu quantity squared over 2 sigma squared. Then the mu's cancel up on the top, and this sigma squared cancels with this sigma squared, and this sigma will cancel with the square root of sigma squared. So we get 1 over square root 2 pi e to the minus t squared over 2 which is the PDF for a normal distribution with mean mu equals 0 and variance sigma squared equals 1. So x minus mu over sigma does have a standard normal distribution. So here we're briefly going to look at the bell curve, or what the shape of this PDF looks like. So for a normal 0, 1, this is a standard normal. This is what f of x looks like, which was what 1 over square root 2 pi e to the minus x squared over 2. And it has this shape, which is a Gaussian or bell curve. It's symmetric about 0, and it goes down to 0 pretty quickly on the left and right. In fact, by the time you get to -3 or 3, it's almost at 0. So most of the mass is between -3 and 3. For a normal 0, 2 random variable, that's very similar. So I have in gray here a normal 0, 1. And what happens whenever you increase the variance, it makes the curve spread out. So it gets flatter and wider. And then I also show what happens if you change the mean. So for a normal 1, 1 random variable, that would be increasing the mean by 1. That shifts it to the right, so that the curve is now centered above 1. And we have the standard normal table, which I will show you how to read soon, whenever we get to an example. But this is the probability that z is less than or equal to a particular number, I'll just call it t, for a given t. And you can use this to solve probabilities for all sorts of normally distributed random variables. So for an example, let's let x be normally distributed with mean 3 and standard deviation 2. We want to find the probability x is less than 4, the probability x is bigger than 2, and the probability x is less than 0. So for each case, we're going to normalize the random variable. Since it has mean 3 and standard deviation 2, we're going to subtract 3 and divide by 2. So the probability x is less than 4 is the probability x minus 3 over 2 is less than 0.5, and that's by subtracting 3 and dividing by 2 on both sides. And then this is a standard normal, so it's the probability z is less than 0.5, where z is a standard normal. So to find that, we go to our table, and this is the row with 0.5, and this column determines the second digit. So it's 0.500, which has this value, 0.69146. And so that is the probability x is less than 4. It's equal to 0.69146. Next, let's find the probability, that takes care of 1, so we're on 2. The probability that x is bigger than 2. So again, we standardize. The probability x is bigger than 2 is the probability x minus 3 over 2 is bigger than negative 0.5, where the probability z is bigger than negative 0.5. Now this is a standard normal. So if we go back up to this bell curve, and we look at negative 0.5, and we want x, the probability that z is larger than that, so the area under this curve, we can instead flip that around and look at positive 0.5 and look at the probability z is less than positive 0.5, or the area under this curve, because those two areas are going to be the same by symmetry. So we're looking for the probability z is bigger than negative 0.5, which is equal to the probability z is less than or equal to 0.5. So again, we get 0.69146. And finally, we're going to look at the probability x is less than 0. So the probability x is less than 0, if we subtract 3 and divide by 2, is the probability x is less than negative 1.5, or the probability that z is less than negative 1.5. So if we go back up to the graph again really quick, we're looking at negative 1.5, and we want the area under this curve. The probability z is less than that. So by symmetry again, we could look at the probability that z is bigger than positive 1.5. But the chart doesn't tell us that. It tells us the probability it's less than certain values. So instead of finding the probability it's bigger than 1.5, we could find the probability it's less than 1.5 and take 1 minus that. So 1 minus that would give us the area over here. And so that's what we're going to do. You go back down to this example. And we're going to take 1 minus the probability that z is less than or equal to 1.5. So the probability z is less than or equal to 1.5 we can find from the chart. We're going to go to the row that has 1.5, and then it's 1.50, so we're looking at the first column. If it was 1.51, we'd go to the second column, or 1.52, we'd go to the third column, and so on. But it's 1.50, so we look at the first column, which is 0.93319, and we want to take 1 minus that. So we're going to take 1 minus 0.93319, which is 0.06618. So you can find the probability of any normally distributed random variable by using this table for a standard normal and by standardizing the normal distribution, the normally distributed random variable.